Hi, this is the introductory lecture for the artificial neural network, and we will go over some of the basic concepts and more advanced topics in the lectures to follow. Okay, so we will go over the definition of the artificial neural network, the structure, the applications, computing the output, examples, mode of operations, and design parameters, not necessarily in the same depth, but we will try to cover those key concepts. The artificial neural network is, let me pick up a nice color here, is inspired by the neural connections in the human brain, okay, as you can see in this diagram, where the neural network nodes represent neurons. Okay, so you can tell right away that in a neural network we will have nodes, and the synapses in the brain will be represented with connections. So we will mimic the neurons and their synapses with nodes and connections. And typically, the artificial neural network is used in supervised learning, but you can see some apps for their used in unsupervised learning. There are there is the basic one that we'll cover in this lecture and the following lecture, but there are other variations. Convolutional neural network, for example, recurrent neural network, deep neural network, and I can tell you from now that these are very hot neural networks used for example, face recognition in the detection systems. The neural networks and its derivatives is very popular. There are many software and tools written for these models. Okay. The structure of a neural network, basically we have input and output, like any computing system, and the input fans out with connections to internal nodes, as you can see right here. Let me pick up a pointer here. Perhaps I would check a highlighter. So you can see these connections between the input and internal nodes. And these internal nodes, we will call it, they are part of the hidden layer. And the hidden layer of the nodes, they as well fan out to the output nodes. Okay, so you can see here in this particular example or structure, we have one layer of hidden nodes, and that's why we call this neural network single layer. Obviously, very shortly, we will see that these connections will have weights, right? Also, these nodes include biases and activation function, as you will see, okay? And all those add to the criteria and the magic of a neural network and how it works. Okay. Let's see next here. If we have more than one hidden layer, like in this case, then we have a multi-layer neural network. You can see the same structure here: input, output. These are very common as a single layer. Okay. But in this case, instead of one hidden layer, we have multiple hidden layers. People sometimes refer to more than 3 hidden layer neural network as deep, 3 or more as deep neural network, and this is these terms are not really very let's say scientific, but some folks like to refer to networks with 3 layers or more of hidden layers as deep neural network. The structure, as we said, is the same. You have input, output, connections between the input to hidden layer, between hidden layer to hidden layer, as we can see here, from hidden layer to hidden layer. These are connections, okay? And at the end you have the output. This is of course the connections have weights, the nodes have biases that will be added to computations, and the result will be applied to an activation function. Okay. Now you can see the main applications for neural network is really in supervised learning. You can use them for regression, classification, more so in classification than regression. Now you might ask the question, what's the difference between using neural network and the regression model that we explained in few classes earlier, which is the linear regression? And the answer is very simple. Neural networks can model nonlinear regression. Okay, so for example, in this case, you have some kind of nonlinear pattern here. You don't have this nice linear behavior where I can model these points linearly. This is completely nonlinear here. So the neural network can be used in regression to model nonlinear behavior. But more so, really, they are very powerful in classification. In our discussion here, we would really we can see that regression and classification, they both for us mean the same thing. After all, we are trying to train the model to fit a line or classify nodes. So you can see that the regression model can really be easily converted to classification. So for example, you can conveniently say that if the regression output is greater than 0.5, you will consider this as a 1. For instance, in a single input in a single output neural network. And if the output is less than 0.5, you can say that this represents for you a 0. So basically, the usage of regression or classification both interact. Of course, as we explained earlier in the course, that the main difference for as an output, the main difference between regression and classification is the fact that regression, the output is continuous. In regression, the output is continuous. In classification, on the other hand, the output is discrete. So these are the two. This is the main distinction between the two as far as the output or result is concerned. Okay, so let's move on. I've seen in one of my references here this interesting explanation of neural network, and it says that the neural network really what it does in the when you train it and it fine tune these weights, what it does is really it kind of stretches the stretches and squashes the data space, and in this case, if you try to draw a line here, it is very difficult because our objective here is to separate the red data from the blue data so that we can predict which is red and which is blue. As it stands right now, you cannot do that. So what neural network does, on the other hand, it stretches and squashes the space in such a way that it is easy to draw this separating line. Okay, so some people really would like to think of neural networks as a smart spreadsheet. Of course, there is more into that than just spreadsheets, but okay, so they involve really some kind of manipulating the space of data to make classification of data easy. Okay, so now we discussed the applications and the theory. let's talk about how we compute the output of a neural network. So let's go to a diagram here. So basically here, any node in the or let's just back a little bit. Computations are done in the nodes of the neural network. So any node has data coming from either previous layers, nodes, or primary input. Okay, so you can see here, so this is data here coming either from the input or previous layer nodes, and as this data travel to the node, there are weights here. There are weights on every connection. And so what we do, we multiply the data by the weight. Okay, we multiply the data by the weight. And then inside the node here, what we do is that we sum these results of multiplication of data and nodes. So you can see we sum them here. So this result is here, this result is here, and this result is here. So once we sum them, we add to them a bias, and this bias is inside every node. Okay, and all these weights, right? Let me just change color here. All these weights and biases are determined or calculated during training. What we're doing here is what is referred to as forward computation or inference, and in this case we assume that we already have those weights and biases computed. So once we compute this quantity right here, and now what we do is you can see it right here, this number here, we take this result and apply it as an input to activation function. The activation function basically has the job of transferring the linear behavior, because so far what we have seen is that we are multiplying weights and adding biases. That is linear. Now to change from linear to non-linear, here comes the job of the activation function. If we don't have activation function, then we don't have non-linearity feature for the neural network. And neural network magic really is based on their ability to model non-linearity. Okay, so where is the activation function? In this case, this is the activation function. There are multiple of them. There's the sigmoid, there is ReLU. We'll see some of them right now. But what they do, you have an input here. Okay, you plug it in. Okay, the input in the x-axis, and you get a result in the y-axis. Notice in this case, this activation function. If I draw this a little bit, this activation function here, what it does is, let's see if I get my pen back. The activation function basically, let's see. Okay, change. I didn't draw it very well, but it's something like that. So the maximum value here is 1, and the minimum value here is 0. And so you can see this is the x-axis here, and this is the y. So this is basically this sigmoid function is if you have your output basically limited between 0 and 1, and by the way you have many variations of those. You can have the output vary between minus and 1, or between whatever you want. You can change those parameters. So and right in between here, where and during small values, this nonlinear behavior for this activation function. Now we plug in our, as we said, we plug in our input, then we get the result here. This result of the activation function is 0.73. This now is the output of this node, which will be directed either to the next layer, or this is the result of this node if it is an output node. So this whole thing here, as you can see, is one layer. Okay, so now what we just did right now, we zoomed in on the one layer computation. It's important that we understand this very, very well. We started with data coming from primary inputs. We ended up with results computed either to the output or to the layers that are in the next level. Weights and biases are to be determined and computed during training. Okay, those are the parameters. Okay, this is another example here. I'm not going to go over it. It's very similar. Okay, now activation functions, those are what we said, they are the ones that introduce nonlinearity. Okay, so the nonlinearity really comes from using activation functions, and people have spent lots of research work on those activation functions. I'm just giving examples of those. So you've got here the step function. Okay, let me talk about the common ones. The most common one is the ReLU here, the rectified linear unit. People like to call it ReLU. And basically what this one does is that this is the x-axis unit, this is y-axis. Or you can say it's the fx. Okay, so for negative value, the result of the output is 0. Okay, if x is 0. Now if x is greater than 0, the output equals x. That's simply the ReLU. Now for the second most common one is the sigmoid. And this one is has the output, as we have seen in the earlier slide. The output is limited between 0 and 1. As you approach infinity, it is 1. As you approach minus infinity, it is 0. And right in between here, you get intermediate results. Okay, so your output never exceeds 1, never below 0. So it saturates between these two. So this is the range of your output. Notice the ReLU here, on the other hand, the minimum value of 0, but the maximum value you can have as much as the x value. There's this soft plus here, which is very close to the ReLU. So the ReLU here is like so, but the soft was comes smooth in its approaching the x equals 0. And of course, this is coming from this function here. Okay. And you can see there are other activation functions, the step, the tan, many activation functions, but mostly we will focus in this course on the ReLU and the sometimes the sigmoid activation function. Again, what is the value of the activation function? They introduce non-linearity modeling into neural network. That's very, very important. I can't stress this anymore, because if you really miss this point, you missed a huge detail about neural networks. Otherwise, if we don't have these activation functions, the neural networks really they are linear transformation. And in linear transformation, you cannot model nonlinear behavior. Okay, so here's an example here. We'd like to look at an example of a neural network, and we will try to line fit and classify at the same time. And for us, line fitting and classification, they kind of converge. You can take the results of regression and assume if it is above a certain value, you can call it a 1, or below a certain value, you can call it a 0. So basically what we have is that we are trying to model the productivity of versus working hour. So from 0 here and this axis all the way to 1. We'll assume 1 is 24 hour. Okay, and 0 hour. So we took 9 data points from people worked different period of times, and we measured their productivity. I don't know how we measured it, but we assume we measured somehow. Okay, and we found out that people who spend very few hours, their productivity is low, and then if they work at up to 8 hours, their productivity is high. Probably these type of jobs like study or some kind of skillful job, it needs sometimes to perfect the work in your shift. So you have to spend really good time to get things working in a very productive way. So half an hour doesn't work, 5 minutes doesn't work. But if you spend 8 hours, then you seem to start really becoming productive. But if you exceed 8 hours, we found out that people who go overboard, so if they approach 24 hour or 22 or 20 hours, then their productivity drops down. Okay, so whatever example. So here's an example. And of course, there is no way you can model this in a linear way. There is no way. Okay, because in linear regression, we have seen that points are aligned in a nice way for a line to come in and fit the data. But there is no fit. So in this case, what we desire to create a neural network to classify a work as productive if the output approaches 1. Okay, or non-productive, the output approaches 0. At the same time, you can say that we are trying to line fit the data. It's the same thing, okay, because it is really the same model. The way you would like to interpret the output, it makes it classification versus linear regression, because in this case we have really one single output, which is productivity in this case. So if you consider productivity as a continuous output, then you look at this problem as a regression. If you look at productivity as a 0 for non-productive and 1 as productive, you classify the output, then this is the classification problem. Okay, well, it's the same model, we'll see. Of course, there is no way you can classify this with linear data. So forget about linear predictors. They're not going to do the job. What we did, we decided to use a neural network with single layer neural network with single input, which is the number of hours, and single output, okay, which is the productivity. And in this case, we ran our training, and we found out certain weights. Okay, let's see if I have in the other side here. Okay, so here are the weights, right? So you can see this input goes to this node. So this is node 1, node 2, and the bias of node 1, the bias of node 2, and the activation function for each node is the ReLU. And then each node will send out its output via connection to the results, and these are the weights for. So you can consider this as weight 1, weight 2, weight 3, weight 4, if you like. Okay. All right, so let's see how the computation is done. So in this case, we will assume that we have a working hour of 0.05. Very small amount of time. And we know ahead that this should give you a classification of no productive or a very low result. Okay, so what we do, we take this input, we multiply it through this connection with this weight, Then we add the bias of the first node, okay? Then the result here we apply to ReLU, and the ReLU result is 7.6. At the same time, we go to the other connection here. Let me choose another color here actually. We go to the other connection. The weight here is minus 1.58. And this is the result of multiplying the input with the weight. We add the bias here, which is 1.45, which is the result of 1.37. We apply it to the ReLU. So you can see, by the way, here this is going to the node 2. So this is node 1 and this is node 2, and 1.37 we apply it to the ReLU, and the results will be 1.37. Then the output of the first node and the second node, we apply the we multiply them by the connection weights, okay, and then we sum them at the output. And this is the output node here. We don't have bias here for the typically single layer node. They don't have biases. Okay, you can conveniently break this rule if you wanted to, but so now we add the results here, and we get a result of 0.15. Okay, if you recall here, so 0.15 is very low, and we can classify this is 0.15 between 0 and 1. This is close to 0, so we can classify this as not productive. Okay, so a working hours of 0.05 is not productive. So this machine predicted correctly, okay, given this number of hours, what we expect, which is not productive work. So if you look at let's see, if you look at so the data point was picked from here, and you can see that we got a low result here. Okay, all right. Now we can think of in terms of regression. If we take this model and this point here, we apply this. This is the input x values from zeros all the way to 1, and obviously we start doing certain plots here. So we take these values, we multiply it by the weight, and add a bias, and then apply it to a ReLU. We will see that we will get this type of curve or a plot. Similarly, here on the other side of the connection, if we multiply the input, which we vary it from 0 to 1, by this weight, and we add a bias, we'll have this kind of plot here. Okay, now you can see that this one of them is flipped, and the reason of the flipping, notice that in fact both of them are flipped because of this negative sign here in the weight, negative sign. Okay, all right. Then what we do here, and we take this curve and we multiply it with this weight, and then we take this curve and multiply it with this weight, and then we sum them, we get this final curve. All right, and so do not be confused with these intermediate curves. All what we did, we take the value for x and we evaluate it at different points, maybe at 0.0, 0.1, 0.2, 0.3, 0.4, all the way to 0.9, 1.0, and then we plotted these curves as we vary these x's. Okay, so this is the final curve right here. Okay, so if we look at the here, you can see that this is our final curve, right, of the output. And interesting, so this curve, what it does is trying to fit the initial training data that we started with, and we will talk about training later on. In other words, what we did, we did both classification and nonlinear regression at the same time using the same model. Again, how am I going to interpret the data? Well, I can use other let's say nodes to classify the output to 0 and 1, or functions, but in this case I'm gonna take things very simple. If it is above 0.5, I will consider this as 1 or productive. Below, I will consider this as 0 or non-productive. Okay, so you can see our model classified, and our model line-fitted nonlinear data. Okay, modes of operation of our neural network. Now, we talked about the parameters, and basically those are the W's and the biases, okay? And those are really, where did we get them? Well, we compute them during training for the data. And during training for the data, during training the model, we use some of the data. So initially, here is my data, and I mean by my data is that the labeled data. Then I split them into training data and testing data. And the training data is used to train the model and compute these weights and biases. Once I compute them, I test my model by applying the test data and see, am I predicting things correctly? Okay, am I getting the predicted results? Okay, so in training, it involves forward propagation and back propagation, and we'll talk about those in particular the back propagation in later lecture. In testing, we use the trained model on test data, and you can think of it as data that we can label, or if it is a data that we have already labeled, we can measure the accuracy of the model. Okay, so this test data can measure the accuracy, or now you are using it on the field to make sure that you can recognize the faces and apply basically the application. Okay, important for neural network is the design parameters here. How many layers, how many inputs, the type of network. We'll talk about those max pool and softmax and all that. So basically, in other words, in an essence, really, the neural network design sounds like a menu in a fancy restaurant, and you have all these options for you to choose from, but obviously not any combination of options will give you a optimum performance. So you really have to be seasoned researcher and engineer in the neural network field for you to say, well, it has to be 3 layers. We need to have in the first hidden layer 10 nodes, and the second one 5 nodes, and the third. So you and then you go, you simulate, and you find out the optimum architecture for you that gives you the best accuracy for prediction. Okay, so basically, whether it's a classification or linear, nonlinear regression, you are trying to predict something. All right. Okay, I will leave you at the end here with some applications of a neural network. Some people reported using neural network as encoder decoder. So in this case, you really have the neural network receiving an input, and it will try to encode it, and then you have another set of layers, or one layer, which decode. And in this essence, really, what you are trying to do, you are doing dimensionality reduction. You are encoding, okay, and then you are expanding back. So you really having the capability of neural network to be able to, or to help you to encode or perform dimensionality reduction on your data. There's another application here. I will leave it for you. Basically, what we have covered in this lecture is the fact that where neural network came from. It came from really they try to mimic the way the brain is structured. And they can be single layered or multi-layer, and we looked at in every layer there are nodes, and these nodes receive data via connections, and these connections are weighted with some weights, and there are these computations that happens in every node. It multiplies the connections by their weights and add the biases, and then we apply the result into nonlinear into activation function. You do this in single layer or multi-layer, however many layers you have, and then you compute your output. You can use the model to do nonlinear fitting, line fitting, or you can use it for classification. Now, obviously, we have indicated that in the modes of a neural network, you can use it for, first of all, you start with a data, and this data you split it into training data and testing data, and then the training data you use it to compute the weights and the biases, your parameters. And then once you computed those and you prepare the model and you're happy with the error that you are getting and the accuracy, then you take the model and you apply the test data, and that's when you get your really accuracy numbers from the test data. And in the next lectures, we will talk about backpropagations and other features of neural networks. Thank you very much.